Alright, ladies and gentlemen, this is going to be the next video on organic compounds. So let's get started on this next video. So what is an organic compound? Well, we're going to have to think about the four molecules of life before we start really delving into this. Now we can break down organic compounds basically into four categories. So the first one that we're going to go through and talk about are carbohydrates. And these are going to be things like glucose, fructose, starch, and cellulose. When we think about carbohydrates, these are really sugars. As a scientist, when I think of carbs, I'm thinking of sugars. The next molecule that we're going to go through and talk about is going to be, in this case, nucleic acids. And nucleic acids are either DNA or RNA. And in this case, they are holding the blueprints or all the directions that we need for life on Earth. Now, the next molecule, the third, is going to be lipids. And lipids are going to be anything like fats, oils, steroids, maybe waxes. And these are the things that are going to provide long-term energy storage and then also have lots of biological functions in our body that we will talk about when we get to cells. You can kind of think of this as like any of the oils that you would find in your kitchen that you would use for cooking. Now, lastly, the last one that we're going to go through and think about and talk about here are proteins. And proteins are enzymes, maybe they're for structural or for movement. They're in your muscles and they might be there for protection, but they're really anything else that is going to make up your body and then provide mass for your body to go through and function and maintain homeostasis. So we can think about proteins maybe like fish or chicken. You might think of eggs, dairy products, any one of those things are going to be proteins. So let's continue upon organic compounds here. There's over 11 million organic compounds out there on Earth. And in order to be an organic compound, it has to contain a carbon to hydrogen or carbon to carbon bond. Now, if we have a carbon to hydrogen, a carbon to carbon, and we also have a nitrogen, an oxygen, a sulfur, a phosphorus, or any other halogen, it's still considered an organic compound. But at a minimum, we have to have a carbon to hydrogen or a carbon to carbon bond. Now, if we're going into this a little bit deeper, well, the simplest organic compound that we can think about here is going to be methane, CH4. And the most complex that we're going to think about here is DNA. And DNA is really the most complex organic compound because it's containing all of that information necessary for life. So how do we go through and identify what an organic compound is? Well, here's the thing. We have to understand carbon first. So carbon has 6 protons and 6 electrons. And as we go into this, we can see in the first shell, if we're following the Bohr model, there are 2 electrons. And then the second shell, there are 4 electrons. Now here's the thing. So these 4 electrons are really important because those are the 4 valence electrons, the electrons in the outer shell. Now because of that, it opens up bonding slots for carbon. There are 1, 2, 3, 4 slots for carbon to go through and bond covalently. Now if we have an atom that has less than 4 electrons in the outer shell, generally they're going to form ionic bonds and try to get rid of those electrons and form an ionic charge, form an ion, and then form an ionic bond between the 2 atoms. But carbon has only 4 electrons in its outer shell, or the valence shell. Therefore, it's going to form covalent bonds, and those covalent bonds are going to go through and give up to 4 bonding slots. Now, this is the reason that carbon is the backbone for all organic compounds. It has to do with the ability to basically give the freedom and increase the ability to bond covalently to other molecules that exist in nature. So if we're going through and trying to understand organic versus inorganic, well, again, we have to understand carbon here, but we can classify it in these 2 categories. So all compounds are either organic or they're inorganic. Now, if we have an organic compound, well, in this case, it's going to have to include a couple of things. It has to contain carbon bonded to hydrogen and oxygen, or just to hydrogen or carbon itself. And if it doesn't, well, it's non-organic. Now, the chemistry of carbon is essentially the chemistry of life. So understanding carbon is understanding the chemistry of life. Now, let's say it was an inorganic molecule. Well, it's inorganic if it has the following characteristics. So anything that lacks a carbon-hydrogen bond is considered inorganic. So we have to have this carbon-hydrogen bond. It can have a carbon-hydrogen-oxygen, maybe a carbon-hydrogen-nitrogen, a carbon-to-carbon, but really it's inorganic if it's lacking that carbon-to-hydrogen bond or has any metals in that substance. So when we're talking about carbon bonding, well, carbon can form straight chains, branch chains, or rings. So let's look at a couple of the examples here. Let's say we were looking at butane. Butane is going to have 4 carbon backbone, and it's going to have the hydrogens associated with that. So we can also go through, we can look at this molecule here. We can have a much larger chain, and we can see that there's single and double bonds, and the hydrogens and the hydroxyls associated with this. We can see the single bonds represented here and the double bonds represented here. Again, this is another example of a chain. We could also have something like isobutane. Isobutane, we have a carbon coming off of the 3 carbon backbone here, and therefore we're going to have a different shape. And because of that shape, it's going to have a couple of different effects chemically. Now we can also have ring-like structures. So in this case, we have a ringed carbon structure, which is again going to have different characteristics and different properties, dependent upon the quantity of double bonds, single bonds, whether or not it's in a ring, whether or not it's an iso series molecule, whether or not it's got the straight chains, whether or not it's got kinks. This is going to affect boiling point and how it interacts with other things in your body. So if we're looking at the structural formula, let's say of isobutane, well, we can represent it basically in a few different ways that you're going to see in this course. So these 3 models represent the same molecule. In the top right, we just have sticks here, in case these are just lines, or in this case, these are just lines. So what we can do is represent the hydrogens, and we can kind of draw it out in shorthand. Instead of drawing like the bottom model here with all of the different bonds and all the different hydrogens, we can represent it with just the stick model here. We can fill in the carbons and hydrogens, but not actually draw the lines. We can also go through and represent it 3-dimensionally with our ball and stick model here. So in this case, I just want you guys to understand that there's a couple of different ways and different models that we're representing different molecules here. And all 4 of these molecules are right, but they're representing different things, or they're giving scientists the ability to write it faster. So let's think about the arrangement of organic compounds then. So we can have organic compounds that are called isomers. And isomers are compounds that have the same molecular formula, but they have different structures. So here's the thing. Let's say we have C6H14, so a molecule with 6 carbons and 14 hydrogens. Now we can represent it like this. We can have a 5 carbon backbone. We can also have a 5 carbon backbone with a carbon coming through the middle carbon, or the 3rd carbon here. On the left, the carbon chain is coming out of the 4th carbon. We can represent it like this, where we have a 4 carbon backbone, and then on the 2nd carbon, there are 2 carbons going through and coming out of it. We also can have a 4 chain like this, and we can have 2 carbons coming out of number 2 and number 3 carbon. So here's the thing. The more carbon atoms in the formula, the more isomers. So when we're talking about isomers, you have the same number of atoms, but the arrangement and the shapes are different. Now this is really important when we're talking about differences in properties. We can see we have butane and we have isobutane. Same number of carbons and same number of hydrogens here, but because the shapes are different, they have different melting points, boiling points, and densities. And the shapes are going to affect the polarity. Remember, alcohol and water don't boil at the same rate because of the polarity of the 2 liquids. The shapes will affect the polarity, just the same way that the shape of water affects the polarity. Butane and isobutane have different shapes, therefore they have different intermolecular forces and different polarities, therefore it's going to affect their boiling point, melting point, and densities. So when we're talking about this, I've used the word hydrocarbon. And all a hydrocarbon is a molecule that only contains carbon and hydrogen. So if we were looking at these, we can think about the common hydrocarbons here. There's methane, ethane, propane, butane, pentane. And we can go through and represent these by how many carbons and hydrogens there are present and if they have single or double bonds. So we'll go through and talk about naming hydrocarbons in another video, but we can see, dependent upon the number of carbons there are, you're going to have different names for each of the molecules here. And all a hydrocarbon is just a carbon with only hydrogens in its actual molecular formula. So let's go into carbon bonding then, just so we understand hydrocarbons and organic molecules. Now, when we're going through and talking about this, we have a single bond. Now, a single bond is one covalent bond between 2, in this case, it's going to be carbon atoms. So what's going to happen is the carbons are only going to share 1 pair of electrons, or 2 electrons total. Now, if we were to represent this on paper, it would look something like this. Now, next we have a double bond, and this is 2 covalent bonds between 2 atoms. So in this case, we have the same carbons, but instead we're sharing 2 pairs of electrons, or 4 electrons total. this bond is going to be slightly stronger and slightly smaller. If we're representing it on paper, it's going to look just like this. Now, lastly, we can have a triple bond. And this is 3 covalent bonds between 2 atoms, or the 2 atoms we're talking about here are carbon. Now, this is exactly what you would think it would be. It's sharing of 3 pairs of electrons, or 6 electrons total, and therefore we're going to get 3 bonds. And we would represent those 3 bonds just like this. So the strength and then the length of the bonds are going to be affected by how many electrons are shared. A single bond, there is more distance in between the 2 carbon atoms. It's the longest and the weakest bond. Now, a double bond is going to be somewhere in the middle. It's going to be medium in length and medium in strength. So again, we're sharing 2 pairs of electrons here, so 4 electrons total. The distance is going to be a little bit closer than a single bond, not as close as a triple bond, and it's not going to be as strong as a triple bond, but it's going to be stronger than a single bond. And lastly, we have a triple bond. And a triple bond is going to be the shortest and strongest of the bonds because, again, we're sharing 3 pairs of electrons here, or 6 electrons total. And it's also going to pull those carbon atoms in a little bit closer. So let's say I'm going through and we're looking at a model here. So let's say the purple represents a carbon atom. Now here's the thing, carbon can hold up to 4 bonding slots here, 4 bonding slots total. So we can add 1, 2, 3, 4. In this case, these might be hydrogens here. We can add 4 single bonds here. Now here's the thing, let's say I remove all of these. Let's say I put in 1, 2, 3, 4 triple bonds here. So here's the thing. Does this atom, would this exist in nature, and does this follow our rules of 4? Well, here's the thing, it doesn't. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total bonds. And in this case, remember, that would have to be sharing 24 total electrons here. And that would not work. We can only share 4 slots, or up to 8 electrons being shared total. Remember, we can only hold 4 slots. Right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 here. So in the case, if I had a triple bond between a carbon and a carbon, I would only be able to add a single bond with maybe a hydrogen in order for that molecule to function or to exist. Remember, 1, 2, 3, 4 total slots that we can go through and bond with. Now let's say I had a double bond, I can add 2 single bonds for a total of 4, or if I had a double bond, I can add another double bond. And then again, if I have single bonds, I can add up to 4 of these single bonds total. And in this case, I would get a tetrahedral molecular geometry here. And again, dependent upon the single or double bonds, it's going to affect the polarity and how the molecules interact with each other. So when we get into single and double bonding, well, this is going to affect the hydrocarbons. So there are 2 types that we're going to go through and talk about. They're going to be really, really important for us to understand when we start talking about lipids. So when we're talking about saturated hydrocarbons, these contain all single bonds between the carbon and hydrogen atoms here. So say I was looking at this image here, what I can see is this is going to be less reactive, and it's saturated because there are only single bonds between the carbons. Now let's say I was looking at an unsaturated hydrocarbon here. Well, in this case, this contains at least 1 or more double or triple bonds between the carbon and the hydrogen. So if I'm looking at this image here, what I can see is I have a double bond. And this is going to create a kink. It's not a perfectly straight chain of carbons now. Because of that, when you go through and pile these molecules on top of each other, they're not going to sit perfectly flush in whatever medium that they're in. This makes them more reactive, and it makes them unsaturated. It's a lot of information in the video. Again, if you do get confused, please come see me during Lunch and Learn, or please go through and just rewatch the video. A lot of this stuff you guys haven't seen. It's really, really difficult information to understand. So it's really, really important that you take advantage of the resources in the course. So did you guys learn what an organic compound is? Did you guys learn why all organic compounds contain carbon? Did you guys learn what hydrocarbons are? Did you guys learn the bonding types, single, double, and triple? And then did you guys learn saturated versus unsaturated? This is going to be the end of the video. I will see you guys in class tomorrow.